Hello student, welcome to my channel Learn Physics. Today I will be discussing the photoelectric effect and matter wave. This one short video will be extremely helpful for your preparation in NEET, Main, Advanced and 10 plus 2. I will also be discussing the previous year question paper of NEET, Main and Advanced. If you watch this video, you can give the answers of all MCQ coming in NEET, Main and Advanced examination. Okay, now let's start. Look at this. This is the vacuum. Okay, this is the cathode. Light incident on this surface. Okay, due to incidence of this radiation, the electron is emitted. Okay, this emitted electron is collected at the anode. Okay, now if anode is connected to the positive terminal and cathode is connected to the negative terminal of a battery, then current will flow. This current is called photocurrent. Okay, look at this. This is the negative potential and this is the positive potential. Plus this is the minus. Okay, no problem. Now first of all, definition. When a radiation of suitable frequency incident on the metal surface, emission of electron takes place. This phenomenon is known as photoelectric effect. The emitted electron, look at this, the emitted electron is called photoelectron. Okay, and corresponding current is called photocurrent. The amount of photocurrent I directly proportional to the rate of emission of photoelectron per second. Okay, now first of all we have to define the important term relating to photoelectric effect. First of all, work function. Work function, the amount of energy required to a metal surface to emit an electron from it is called work function. Its unit is joule or electron volt. 1 electron volt equal to 1.6 into 10 to the power minus 19 joule. We always prefer metal of low work function for photoelectric emission. Okay, such as cesium, whose work function is 1.9 electron volt, sodium 2.3 electron volt. Okay, understood? Now, threshold frequency. Threshold frequency is denoted as nu naught. Okay, the minimum frequency of radiation. Look at this. This is this radiation. The minimum frequency of radiation by which emission of electron takes place is called threshold frequency. Threshold frequency depends on work function. Actually, threshold frequency directly proportional to work function. Greater the work function of the metal, greater will be the threshold frequency. If h be the Planck's constant, then work function is equal to h nu naught. Now, nu naught equals to c by lambda, therefore this is the hc by lambda naught, where lambda naught is called threshold wavelength. What is threshold wavelength? The maximum wavelength of radiation by which emission of electron takes place is called threshold wavelength. Okay, now a numerical relating to threshold frequency. The light of frequency 1.5 times the threshold frequency is incident on a photosensitive material, that is nu equal to 1.5 nu naught. Okay, what will be the photoelectric current if frequency is half and intensity is doubled? Here frequency lambda dash equal to 1.5 nu naught by 2, that is 0.75 nu naught. Okay, this is less than Newton. Therefore, no emission of electron takes place whatever be the intensity of radiation. Okay, now stopping potential. Okay, the minimum negative potential given to the anode such that the photoelectric current becomes zero. If V be the maximum velocity of photoelectron, then half mv square is equal to EV naught, where V naught is the stopping potential. Actually, the EV naught equal to half mv square, this equal to h nu minus W. So from this equation, greater the frequency of radiation, greater the stopping potential, and greater the work function, smaller the stopping potential. Okay, understood? Therefore, stopping potential depends only on the frequency of radiation and work function. It does not depend on intensity of radiation. Okay, now a problem relating to stopping potential. Look at this. A source of light is placed at a distance of 50 centimeter from a photocell, and the stopping potential is found to be V naught. Okay, so V naught is the stopping potential. Now, if the distance between the light source and the photocell is made 25 centimeter, look at this, distance becomes half. Okay, initial distance becomes, so look at this, 50 centimeter is the initial distance. Now final distance 25 centimeter, so distance becomes half. If distance half, so intensity I proportionate 1 by d square, so intensity becomes 4 times. Yes, but stopping potential does not depend on intensity of radiation, so stopping potential becomes same. Okay, now properties of photoelectric effect. Number 1. Okay, the number of photoelectron emitted per second is directly proportional to the intensity of radiation. That is, number 1, photoelectric current directly proportional to the intensity of radiation. If a graph is plotted between the intensity of radiation and photoelectric current I, this graph becomes straight line. Okay. Now, if we draw a graph between potential V and photocurrent I, then the graph becomes, look at this graph becomes like this. This is the intensity I1. Look at this is the intensity I2. Okay, and look at this is the intensity I3 radius. Look at this here, I1 less than I2 less than I3. Okay, so so look at this, smaller the intensity, smaller the photoelectric current. Okay, and look at this voltage, look at this voltage represents the stopping potential V naught. Look at this, stopping potential V naught does not depend on intensity I1, I2, I3. All have same stopping potential, because stopping potential does not depend on intensity, it depends on frequency of radiation and work function of the metal surface. Okay, now properties 2. The maximum kinetic energy of electron does not depend on intensity of radiation, it depends on nature of the radiation, that is frequency, and nature of the metal surface, that is work function, from where electron is emitted. Look at this, so half mv square, this equal to, this is the h nu minus W. Okay, now look at this, number 3. The minimum frequency of radiation by which emission of electron takes place is called threshold frequency. No emission of electron takes place if the radiation frequency less than the threshold frequency. Okay, now number 4. Number 4, it is the instantaneous process. That is, there is no time lag between incidence of photon and emission of electron. Okay, and number 5, it is independent of temperature. Okay, and number 6, the velocity of photoelectron ranges from 0 to a certain maximum value. Okay. Now we have to draw a graph between the radiation of same intensity but different frequency. Now look at this. This is the V. Look at this. Suppose the new one is smaller frequency. So look at this. This graph becomes like this. Okay. Now this is the for new one. So here stopping potential. This is the V1. Okay. Now another frequency nu 2. This is greater than nu 1. Okay. Nu 2 greater than nu 1. So look at this here. Stopping potential for nu 2 is more. Okay. Now another frequency nu 3 which is greater than nu 2 and nu 1. So look at this, all have same intensity, so same current, but look at this, stopping potential is different. So greater the frequency of incident radiation, greater the stopping potential. Okay. Now some important numerical relating to these properties. Okay. Now look at this. This is the very simple question and this can be answered with their properties of photoelectric effect. Look at this. The figure shows the plot of photocurrent versus anode potential for a photosensitive surface for three different radiation. Which one of the following is correct statement? Look at this. Here A and B having same stopping potential. Look at this. A and B have same stopping potential. Okay. And C has different stopping potential. The stopping potential of C is greater than the stopping potential of A and B. So obviously frequency of C is greater. Okay. BC, nu C greater than nu B. So look at this, nu B, nu C greater than, this is the nu B equal to this is the nu A. Okay. And intensity, look at this, intensity for IC and IB are same, and these are greater than the intensity for radiation A. Okay. Now look at this. The curve A and B represent the incident radiation of same frequency. Now look at this. A and B represents the incident radiation of same frequency but different intensity. Okay. This is the correct option. Look at this. A and B different intensity, IB greater than IA, but nu B greater than nu A. Okay. Understood? And the curve B and C represents the incident radiation having different frequency. Look at this, B and C. Look at this, B and C different frequency. Okay, B and C and different frequencies. Correct? And different intensity. No. They have same intensity. Look at this, IC equal to IB. Now curve B and C represents the incident radiation of same frequency. Look at this, B and C. No. B and C have not same frequency. Okay. The cathode of photoelectric cell is changed such that the work function changes from W1 to W2, where W2 greater than W1. That is work function of metal, of work function of second metal greater than work function of first metal. If the current before and after changes be I1 and I2, all other conditions remaining the unchanged, assume H nu greater than W2. Now look at this, current I1 and I2 does not depends on work function. It depends on, current depends on number of electron emitted per second, that is intensity. As intensity same, so current I1 equal to I2. Okay. Now look at this, a photocell is illuminated by a source of light which is placed at a distance d from the cell. If the distance becomes d by 2, as distance becomes d by 2, so intensity becomes I24I. Okay. The number of electron emitted per second, look at this, as intensity 4 times, so number of electron also 4 times. Okay. So option B is correct. Now question number 14. The photoelectron emitted for light of frequency nu higher than the threshold frequency is proportional to the threshold frequency. No. The number of photoelectron emitted, does not depends on frequency of radiation. It only depends on intensity of radiation. So look at this, option B is correct. Okay. Now next question. A photocell employs the photoelectric effect to convert, look at this, the change of frequency of light into the change of electric current. No. The change of frequency of light into the change of current. No. the change in the intensity of illumination into the change of photoelectric current. Okay, so here light energy is converted into electrical energy. Okay, next. Now, quantum theory. Photoelectric effect cannot be explained with the help of wave theory. It can be explained with the help of quantum theory. The quantum theory is the emission and absorption of energy is not a continuous process. It occurs in discrete quanta. The energy in each quanta is directly proportional to frequency of radiation. So energy in each quanta, this is the h nu equal to hc by lambda is called photon. So this bundle of energy h nu or hc by lambda is called photon. Now look at this here. Here hc equal to 1242 eV nanometer divided by this is the lambda. No problem. And h equal to 6.63 into 10 to the power minus 34 joule second. Okay. Or equal to 4.14 into 10 to the power minus 15 electron volt into second. Okay. Now the properties of photon, look at this. The velocity of photon in vacuum is 3 into 10 to the power 8 meter per second. Number 2, the energy of the photon E equal to, this is the h nu equal to, this is the hc by lambda. The rest mass of the photon is 0. Okay, but the dynamic mass h nu by c square. Okay, no problem. Now the momentum of the photon P equal to, this is the h by lambda. Now lambda equals to c by nu. So h divided by c by nu. This is the hc by nu. Now look at this, hc equal to e by c. Therefore e equal to pc. Okay. So energy of photon is equal to momentum of photon into speed of the photon. That is p into c. Okay. Number 4, the rate of photon incident on a metal surface. This is equal to power of the radiation divided by energy of a photon. Okay. So greater the power of the radiation, greater be the number of photon in that radiation. Okay. No problem. Next. 5. Photon collides elastically with the material particle. Okay. Number 6. Number 6. The force exerted by a photon on a perfectly absorbing surface is the power by c. And for a perfectly reflecting surface, this is the 2p by c. Okay. Next, 6 number, photon exert pressure on a surface. For a perfectly absorbing surface, the pressure P equal to I by C. And for a perfectly reflecting surface, this is the 2I by C. Okay. Now some numerical relating to photon's property. Okay. Now, the momentum of a photon of energy 1 mega electron volt in kg per second will be. Now look at this. This is the energy of the photon. This is the velocity of the photon. So P equal to, this is the E by C. Now what is E? E is the 1 into 10 to the power 6 eV. Now if electron volt is converted to joule, so this is the 1.6 in 10 to the power minus 9 joule. Okay, and this is the 3 into 10 to the power 8 meter per second. So look at this. This is the 1.6 by 3 into 10 to the power, this is the minus 21. This is the kg meter per second. Now look at this. This option is correct because here this is the 0.53 into 10 to the power minus 21. So this is the 5.3 into minus 22. So option A is correct. Okay. Now next numerical. The number of photon per second on an average emitted by the source of monochromatic light of wavelength this is the 600 nanometer, when it delivers the power 3.3 into 10 to the power minus 3 watt. Now rate of emission of photon, now rate of incident photon, this equals to n by, this is the power of the radiation divided by energy of the photon. Now what is the power? Look at this, the power is, this is the 3.3 into 10 to the power minus 3 watt. Now energy, look at this, energy is, this is the Hc by lambda. Now look at this is the 3.3 into 10 to the power minus 3. H is the, look at this, 6.63 into 10 to the power, this is the minus 34, this is the 3 into 10 to the power 8, and lambda is equal to, look at this, lambda is equal to, this is the 600 nanometer. Okay, so this is the 600 into 10 to the power minus 9. Okay, now look at this is the 34, look at this is a minus 34, this is the 8, so this is the minus 26. Now this into this almost 20, so look at this, this is the, look at this is the 3.3 into 600. Now this is the 600 into 10 to the power minus 12, and now look at this is the 20 into 10 to the power, this is the minus 26. Now look at this 0 and this 0 cancel out, so this is the 30. Now 30 into 3.3, so this is the 100. 100 means this is the 10 to the power minus 10. So look at this, 10 to the power 16 per second is the rate of emission photon. Okay, understood. Now next, the monochromatic light of frequency 6 into 10 to the power 14 hertz is produced by laser. The power emitted is 2 into 10 to the power minus 3. The number of photon emitted per second. Okay, look at this, the number of photon emitted per second, n equals to, this is the power of the radiation 2 into 10 to the power minus 3 divided by energy, energy is the h nu. Okay, so look at this, 2 into 10 to the power minus 3, look at this, h is the 6.63 into 10 to the power minus 34, and this is the 6 into 10 to the power 40. Now 6.63 into 6 almost 40. Okay, so look at this, 2 into 10 to the power minus 3, this is the 40, and this is the, look at this is the minus 10 to the power minus 20. Okay, now look at this, so here this is the 0.5 into, look at this, 4.5 into 10 to the power 16. Okay, so 5 into 10 to the power 15 per second is the rate of emission of photon per second. Okay, so now look at this, a 20 watt sodium street lamp emits yellow light of wavelength 0.6 micrometer, assuming it to be 20% efficient in converting electrical energy to light. The number of photon of yellow light emit per second. Now first of all we have to calculate the energy of the photon. Energy of the photon, this is the Hc by lambda. Look at this is the 6.63 into 10 to the power minus 34 into 3 into, look at this, 10 to the power 8 divided by, this is the 0.6 into 10 to the power minus 6. So look at this, 6.63 by 20, so this is the almost 20 by 0.6, this into 10 to the power minus 20. Now look at this, so 20 by 6 into 10 to the power, this is the minus 19. Okay, no problem. Now number of photon emitted per second, this is the effective power. What is the effective power? Net power 200, so effective power is the 200 into 25 by 100, so this is the 50 watt. Okay, so look at this is the 50 divided by, this is the 20 by 6, so look at this is the 6 and this is the 10 to the power 90. Now this and this cancel out. Now look at this is 30, so 30 means this is the 30 by, this is the 15 into 10 to the power 19. So look at this is the 1.5 into 10 to the power 20 is the rate of emission of photon. Okay, so look at this, option A correct. With the help of Planck's quantum theory, Einstein explained the phenomenon of photoelectric effect. Einstein told when a radiation of frequency nu incident on a metal surface, the elastic collision takes place between the photon of the radiation and electron of the metal surface. In this collision, electron either absorbs whole energy of the photon or none. If electron absorbs whole energy of the photon, then three possible cases arises. If absorbed energy h nu less than work function, so no emission takes place. Okay, understood? If h nu equal to W, then emission takes place with zero kinetic energy. And if h nu greater than W, then emission of electron takes place with kinetic energy h nu minus W. If V be the maximum velocity of photoelectron, then half mv square, look at this, this is the h nu minus W. This equation is known as Einstein's photoelectric equation. Now look at this, here h nu minus h nu naught. Again, this expression also be written as, look at this is the hc by lambda minus hc by lambda naught, okay, where lambda naught is the threshold wavelength. Now we also know E V naught stopping potential equal to half mv square. So look at this expression half mv square can be replaced by E V naught. So this becomes, look at this, E V naught equals to h nu minus W. E V naught equals to h nu minus h nu naught, and E V naught equal to hc by lambda minus hc by lambda naught. If a graph is plotted between maximum kinetic energy of photoelectron and frequency of radiation, the graph becomes straight line of slope tan theta equal to, this is the h. And look at this point represents the threshold frequency nu naught. And if this graph is produced, look at this represents the work function W. Now another graph is drawn with the frequency of radiation nu and stopping potential, this is the Vs. This graph is also a straight line having slope tan theta equal to, this is the h by E, and this is the nu naught, no problem. And the graph, look at this portion, look at the intercept of y-axis, this represents the work function by E. Okay, understood? Next, now we solve some numerical relating to this. Now, a very important question. Look at this. A photosensitive metallic surface has work function h nu naught. If the photons of energy 2 nu naught, it falls on the surface. Okay. The electrons come out with maximum velocity 4 into 10 to the power 6 meter per second. When the photons energy increase to 5 h nu naught, the maximum velocity of the electron will be. Now look at this. Here V1 is equal to 4 into 10 to the power 6 meter per second. We have to calculate V2 when the energy of incident radiation increases from, this is the 2 h nu naught to 5 h nu naught. Now look at this. First of all, this is the half m V1 square. This is the 2h nu naught minus h nu naught. So this is the h nu naught. Now half mv2 square. Look at this. This is the 5h nu naught minus h nu naught. So this is the 4h nu naught. Now 4h nu naught. This is the 4 into, this is the half mv1 square. So look at this. This is the v2 square equal to 4v1 square. So look at this, v2 equals to, this is the 2v1. Now what is v1? v1 is the 4 into 10 to the power 6. So v2 is the 8 into 10 to the power 6. Okay, look at this, option C correct. Now question number 39. When photons of energy h nu falls on an aluminum plate or of work function E naught, the photoelectron's maximum kinetic energy K. So look at this from here, K equals to, this is the h nu minus E naught. Okay, this is equation number 1. If the frequency of radiation is doubled, the maximum kinetic energy of the elected photoelectron will be. Now K dash equals to, this is the 2h nu minus E naught. So look at this. This is the h nu plus h nu minus E naught. Look at this. This is the K. So this is the h nu plus K is the kinetic energy. Okay. So look at this, option A correct. Now look at this 2011. In a photoelectric emission process from a metal of work function 1.8 eV, the kinetic energy of most energetic electron is 0.5 eV, the corresponding stopping potential. Now look at this. This is the EV naught. This equals to half m. This is the v square. So look at this. This is the E into. So look at this. This is the 0.5 electron volt. So V naught is equal to 0.5 volt. Look at this. This is the option C. Now question number 31. A photoelectric surface is illuminated successively by monochromatic light of wavelength lambda and lambda by 2. If the maximum kinetic energy of the emitted photoelectron in the second case is 3 times that in the first case, the work function of the surface of the metal is. Now look at this. First of all, this is the half mv square. This equal to hc by lambda minus w. In the second case, this is the 3 into, this is the half mv square, 3 times kinetic energy. This equals to hc divided by lambda by 2. So the lambda into, this is the 2 minus w. Okay. Now look at this, put this value here. Okay. So look at this, this is the 3 into hc by lambda minus w. This equals to 2 hc by lambda minus w. So look at this here, 3 hc by lambda minus 3w. Look at this, 3 hc by lambda minus 3w equal to 2 hc by lambda minus w. So look at this here, 2w equal to, this is the hc by lambda. So w equal to, this is the hc by 2 lambda. Okay. Look at this, option C is correct. Now question number 30. When a metallic surface is illuminated with a radiation of wavelength lambda, the stopping potential is V. So look at this, from this equation we can write EV equal to, this is the AC by lambda minus W. W is the work function. If the same surface is illuminated with the radiation of wavelength 2 lambda, the stopping potential is V by 4. So look at this, this is the EV by 4. This is the HC divided by 2 lambda minus W. Okay, the threshold wavelength of the metal surface. Now look at this. Look at this here. Now look at this. This is the EV equal to 4 HC by 2 lambda minus 4W. Okay, this is the EV. This is the EV. So look at this. This equal to this. Okay. So look at this. This is the HC by the lambda minus W. This is the 2hc by lambda minus 4w. So look at this 4w. This is the hc by lambda. So this is the 4 into hc by lambda naught. This equal to, this is the hc by lambda. So lambda naught equals to 4 lambda. Okay. Now matter wave. The total energy of the universe is constant. Okay. And this energy remains in the form of matter and radiation. Radiation possesses material property, that is particle property. De Broglie suggested, as nature loves symmetry, so matter also possesses the wave property. the energy of photon E equal to hc by lambda, and energy E equal to, this is the mc square. Therefore hc by lambda, this equal to mc square. Therefore c and this c cancel out, so lambda equal to h by mc. So this is the h by p. De Broglie suggested that the wavelength of lambda equal to h by p is also applicable for matter wave. So wavelength of matter wave lambda equals to h by p equal to h by mv equal to h by mv can be replaced as, this is the 2me is the kinetic energy. Now E can be replaced by Q into potential difference. So H equal to, this is the 2m, this is the Q into V. Okay. Now E also can be replaced by 3 by 2 kT. Okay. So look at this lambda. Now lambda becomes, this is the lambda divided H divided by, this is the 2m into 3 by 2 kT. Okay. So look at this, this is the h by 3 mkt under root. Okay. For electron, look at this, for electron, if E equals to 1.6 into 10 to the power minus, for electron U equal to 1.6 into 10 to the power minus 19, and mass M is equal to 9.1 into 10 to the power minus 31 kg, then lambda becomes, look at this, this is the 12.22 angstrom divided by root over V. Okay, this matter will be experimentally proved by Davison and Jarmer. Okay, now look at this. Look at this. Lambda equals to h by p. Lambda equals to mv. Lambda equals to 2 h by root over 2me. Lambda equals to h by root over 2mqv. Lambda equals to h by root over root 3 mkt are important relation for solving the numerical. Okay. Now some numerical relating to de Broglie wave. Now question number 7. A particle of mass 1 mg has the same wavelength as electron moving with velocity 3 into 10 to the power 6 meter per second. The velocity of the particle. Now look at this. First of all, wavelength lambda equals to h by, this is the mev equals to h by root over m into v. Now, so look at this here, lambda same. So mass of electron into velocity of electron equal to mass of the particle into velocity of the particle. Now this is the 9.1 into 10 to the power minus 31. V is the 3 into 10 to the power 6. Okay. And mass of the particle, this is the 10 to the power minus 6 kg into V. Okay. So look at this, V is equal to, now look at this, this is the 27.1 into, look at this, this is the 12, so this is the 10 to the power minus 19 minus, so this is the 2.7 in 10 to the power minus 8 with the velocity of the particle. Okay. Now NEET 2020, an electron is accelerated from the rest with a potential difference v volt. If the de Broglie wavelength of the electron is at a nanometer, the potential difference, very easy sum, the wavelength of electron, this is the 12.22 angstrom divided by V root over V volt. Now look at this, this is the nanometer. So look at this here, lambda equals to 12.27 into 10 to the power minus 2 angstrom equal to 12.22 angstrom. This is also angstrom by root over V. Okay. So V equal to, look at this. So V equal to root over V equal to, this is the 100. Therefore V equals to 10 to the power 4. Okay. This is correct. Electron of mass m, de Broglie wavelength lambda falls on a target of X-ray tube. The cutoff wavelength lambda naught of the emitted X-ray. Okay. Now look at this. Here de Broglie wavelength lambda, this is to h by, this is the root under 2me. Okay. So here root over 2me equals to h by lambda. Therefore, E equal to, this is the h square by 2m lambda square. If whole energy of the electron converted into X-ray, then look at this, this is the hc by lambda naught. So look at this, from this equation you can get 2m lambda square. So look at this, lambda not equals to, look at this, this is the 2m c lambda square by h. Okay, look at this, option A correct. Correct. Now another question. The wavelength lambda e of electron, lambda p of photon, the same energy are related as, look at this. Look at this, the wavelength of electron E equals to, this is the h by root under 2me. Okay, lambda of photon P equals to, this is the hc by E. Okay, now look at this, here root over lambda P equals to root over hc by E. Okay, now look at this, so root over lambda P equals to root over lambda E. So lambda P equals to lambda E square. C option correct. Many thanks for watching this video. This video will be extremely helpful for your NEET, main and advanced, as well as CBSE, to get the higher percentile in this entrance examination. Always connected with my channel. Okay, thank you.